Hey guys, so you can probably tell that I'm on, like a Canva whiteboard and I just have a screenshotted problem posted here. But in fact, this problem comes from... So here, it looks like that we're given some sort of differential equation, and we are to find all such functions f having a domain of all real numbers, and that maps to real numbers, such that this equation holds for all real numbers x and positive integers n. Now, this might look kind of bizarre at the start because, well, you might be able to notice that this right hand side looks oddly similar to the definition of a derivative, but without the limit notation. So you might be wondering, is that something we can use, or is that something to just throw us off? Who knows, right? But another thing you might notice is that, well, here n must be a positive integer, and you might be wondering, that's kind of weird, right? Like, what is the point of that restriction? Why can't n just be any real numbers? Now, those are definitely valid concerns, but honestly, when you're just starting out with a problem, it might be best to just play around with it. Just plug in random values, see what the simple structure can potentially offer you. So, in this case, what if we, for example, tried n is equal to 1? Well, the equation would become f prime of x is equal to f of x plus 1 minus f of x, right? And this equation looks a bit more cleaner because there's no denominator, but honestly, we could play around a bit more. So let's just try plugging in n is equal to 2. In this case, we get f prime of x is equal to f of x plus 2 minus f of x over 2, right? Now, at this stage, you might be wondering, should I continue playing around or should I just, move on? I mean, you could continue playing around by testing in n is equal to 3, 4, maybe even, substituting x with certain values, right? But sometimes it is a good idea to maybe pause and think about what you have so far. And in this example, right, notice that with the second equation, you could rearrange it into 2 times f prime of x equal to f of x plus 2 minus f of x. And why is that a good idea? Well, I want you to notice something. Over here with this equation, on the right hand side, we have f of x plus 2 minus f of x. These two inputs differ by 2. Whereas over here with the top equation, we have f of x plus 1 minus f of x on the right hand side. So these two inputs differ by 1. And here's the thing, these two expressions look almost similar in terms of structure. It's both f of something minus f of something, but the structure is definitely different because, well, the inputs differ by a different value. So here's my question to you. How can we potentially manipulate this expression to match the structure of this expression? Take a moment to think about it. So here's the thing in mathematics. Whenever you have certain structures that you want to match, you can often do that by deliberately creating a term. And what I mean by that is, well, you've seen this probably many times, but in this case, we can do this, f of x plus 2, and then we deliberately subtract a f of x minus, not minus, but f of x plus 1. Now, of course, you cannot just minus or subtract for free, you have to add it back, right? So we'll add it back, and conveniently, there is a minus f of x term after. And notice what I've done with this. You might be able to see this right away, but if I were to group these up, well, notice that I've created two expressions that have the structure of this expression. Namely, this expression, well, notice that these two inputs differ by 1, and this expression over here also has the inputs differing by 1. And what does this mean? Well, it means that we can use this entire equation. Notice that this would mean this expression can be written as f prime of x plus 1 due to this equation on top, right? And similarly, this expression can be written as f prime of x. Very cool, right? I mean, we've transformed an equation, or not equation, but an expression about the function f to an expression about the derivative function of f. So that is pretty cool, right? And the best part is that, well, this entire time, this was equal to 2 times f prime of x. So actually, this equation can be rearranged as f prime of x equal to f prime of x plus 1. super simple looking, right? And furthermore, we can rearrange this into f prime of x plus 1 minus f prime of x is equal to 0. And because taking a derivative is a linear process, well then we can write this as f of x plus 1 minus f of x, all derivative is equal to 0. And because your derivative is equal to 0, well then this would mean that f of x plus 1 minus f of x must equal to a constant, call it c, because only the derivative of a constant can equal to 0. Alright, so this is probably going to be very useful. I mean, the difference between f of x plus 1 and f of x must always be a constant value. Might be something to exploit. And in fact, I'm going to zoom out, okay? And here, I still want you to pay attention to the left-hand side of what we derived over here, so this expression over here. And based on what we've done previously, what can you do? What can you replace this expression with? Well, I really hope you thought to look back to the very first equation we've created. This one over here. This one literally has an f of x plus 1 minus f of x. It's literally the same as the one over here, which I told you to pay attention to. And in fact, this is a common reoccurring problem-solving strategy. Continuously exploiting structure within structure is often the way to go when you're just given one simple equation. So in this case, right, as I've said, well, because of this equation, we can definitely replace this expression with f prime of x is equal to c, and because the derivative of f is equal to a constant, well, this would mean that f must be a linear function, so f of x is equal to cx plus d, for c and d being real numbers. So right now, we can tentatively say that this is our solution, and I say tentatively because, well, with functional equations, you always have to plug it back in to see if it actually works, right? Because not all solutions might necessarily work, so you have to plug it back in to check. So over here, let's check the left-hand side if f of x is equal to cx plus d. So left-hand side, this is just equal to c. Now on the right-hand side, this is going to be equal to c times x plus n plus d, right? And then minus f of x, that's going to be minus cx minus d, and then over n. And you can indeed see that this is equal to c. So left-hand side and right-hand side matches, therefore, well, we can just box this as our solution, say that c and d must be real numbers, and this is our answer to the problem. So there we go, we've solved it. But the thing is that to solve this problem, notice that we exploited structure within structure. First of all, we exploited the structure by deliberately creating this minus f of x plus 1 term to match this structure. And then later on, when we got this equation, we went all the way back to over here to replace, well, this entire thing with f prime of x. You want to constantly exploit what is within the structure. I've said the word structure way too many times, so it's about time I end this video, but I really hope you enjoyed it. If you did, please do consider dropping a like and subscribing. Thank you very much. Bye.